This video is a continuation of our dive into the normal curve. We've already seen different types of distributions. We've also seen the empirical rule and applied the empirical rule. And now we're going to talk about z-scores and go through more examples. So one thing that we had talked about in a previous section was the idea of percentiles and how the p percentile of the distribution is a value that has p% of the observations fall at or below it. So I just found out not so fantastic news about one of my nephews. At his last doctor's appointment, he was found to be in the 4th percentile for weight. So we would write that means that um, out of the population of everybody in the exact same age as him, and he was a little bit more than 2 years old, his weight is at the 4th percentile, meaning that most people that age have a much higher weight than he does. He's at the point where only 4% of people 2 years old have his weight. Okay, and so that's a very low weight. If he were in the 90th percentile, that would mean he would be on the higher end of the weight scale for people of that exact same age. Just a little personal spin to it. But this is actually important because what we're going to talk about with the normal curve is we're going to talk about z-scores. And when we look at a z-score, you're looking at a score compared to the mean that tells you what percentage of the data set is to the left of that value. Let's look at an example using percentiles. So we have a table that shows selected ages of licensed drivers in the United States and the corresponding percentiles. So that's all included in this chart. We're going to use the information given by the table to find the percentage of U.S. drivers who are younger than 55. So remember, the percentile tells you at or below. So that's going to be 77%. Okay, younger than 45, that would be 60% of the drivers are younger than 45. Older than 55, well, to find that, we take 100 minus the percentile, which tells us 23% of drivers are older than 55. Older than 45, well, we take 100 minus that percentile, and that tells us that 40% of drivers are older than 45. Now we can say at least 25, so that means 25 and greater. So let me say that again. At least is such a confusing word because people hear the word least and they think less, okay? But that is not how the word actually works. If I say I want to make at least $15 an hour, if somebody came and tried to offer me 10, I'd be mad because I want to make at least $15, which means I want to make $15 or more an hour. Okay, so when I say at least 25 years old, that means 25 years old and higher. So that's going to be 14% is 25 or lower. Okay, 25 years old or lower. So we would take 100 minus 14 and find out that that would be what, 86%. Okay, at least 35, we would take 100 minus 37, and we get what, 63%? 63%. And how do we get the picture about this? We take 100% and subtract if we're trying to find the other side. So let me show you in a picture, because we're going to see this within the normal curve. We're going to see these z values. If the question is asking for this side, it's straight up just like the percentile, okay? It's that exact percentage. So if this side is 30%, then my answer would be 30% if this is the side that we're looking for, the side of the z-score that we're looking for. However, if we're then looking for the other side, so what percentage of people are higher, or what percentage of the data is higher than that z-score, that's going to be 100 minus 30%, which equals 70%. Okay, oftentimes we do this with decimal values. So please don't freak out if it's a decimal as opposed to a percentage. Also, if you've ever heard of p-scores and you hear that the magical p-score to show significance is 0.05, that's essentially saying it's within 5%. Okay, if it's, that's like a very general way of saying that and explaining it, but we might get to that. We'll see. So we've seen with the normal curve, pardon my not great drawing, but we've seen that the values and the percentages between one standard deviation was 68%, within two standard deviations, and standard deviations are the same amount each time. Remember, that's a single value. So try to draw these if you're drawing them as approximately close to being the same width apart as you can. But that represents 95% of the data, and that's within two standard deviations. And then within three standard deviations, that represents 99.7% of the data. Okay, which means that only 0.3% or very little data falls outside of this three standard deviations. So the question on this page is asking us, what do we do if the value that we're looking for is not exactly 1, 2, or 3 standard deviations away? So what if our data point is, I'm going to use blue, what if it's not at 2 standard deviations away, but at 2.3 standard deviations away from the mean? Okay, so the mean value, let me write this up here, it'd be the mean value plus 2.3 standard deviations away. So that's an excellent question. That gets to the concept of z-scores. So a z-score represents the number of standard deviations a data value is away from the mean. So if this right here is one standard deviation away from the mean, it's the mean minus the standard deviation. And then this is the same distance away, so mu plus the standard deviation. And we've already labeled these before, so this is u plus 2 sigmas, u plus 3 sigmas. And again, if we're dealing with samples, they would be s's, but I like the Greek letters, so I don't know. I don't know what I was going to say there. So there, I don't know. It's not a it's not a competition. But anyway, we have these z-scores. But we could have a z-score like right here where it's mu plus 2.3 times the standard deviation. We use z-scores to determine how far, in terms of standard deviations, a given data value is from the mean of the distribution. So if a data value has a z-score of 1.5, that indicates that the value is 1.5 standard deviations from the mean. Okay, the way we find this is we find the distance from the mean over the standard deviation. So then we would say, okay, well, we take the actual value x from our data set and we subtract, in this case, I'm going to use x bar as a population mean, and then we divide that by the standard deviation. So since I'm talking about, sample, we'll use s. Now, if I was talking about a population, we would have x minus mu over sigma. It's the same formula, it's just referring to the population versus the sample. So these are our formulas essentially to determine z-scores. So let's look at a problem. Intelligence quotients are normally distributed with a mean of 100 and a standard deviation of 16. So again, we say that our variable, which is IQ scores or intelligence quotients, is normally distributed with a mean of 100 and a standard deviation of 16. I always like to write this out it helps me remember my mean and my standard deviation from the problem. And that's just a symbol that represents that our variable is normally distributed. It's also a good idea to identify what is your variable. Your variable in this case is the IQ scores, okay? So we're asked to label the times that are 1 standard deviation away, 2 standard deviations away, and 3 standard deviations away from the mean. So it says times. I'm pretty sure they mean IQs. So let's write them. So the mean in the middle is 100. So this would be 116, 132, because essentially I'm just adding 16 each time. These are representing our standard deviations. So then here I would have 148. To get the other values, I would subtract 16 each time. So this would be 84, 68, and 52. So then it asks us, what is the IQ score corresponding to a z-score of negative 1.5? The way we find that is we would say, okay, well, our z-score is negative 1.5, but that's equal to our unknown data point minus the mean, which is 100, over our standard deviation. So I would multiply, essentially I'm solving for x. So we're using opposite operations to solve for this x value, our unknown data point. So we're going to multiply both sides by 16. Then we get, so 16 times negative 1.5 is negative 24, equals these canceled, so I'm left with just x minus 100 on the right-hand side. To solve for x, I'm going to add 100 to both sides. And so we get that our x value is equal to negative 24 plus 100, which is 76. So right here at IQ score 76, that is 1.5 standard deviations away from the mean, or negative 1.5 standard deviations away from the mean. The second part of this question has Mensa is a group of people with high IQs whose members have z-scores of 2.05 or greater on the intelligence test. What is the IQ corresponding to a z-score of 2.05? So again, we're going to do that. Where z-score is equal to 2.05, we're trying to find the IQ value that will give us that standard deviation z-score, standard score. So I take that x value that's unknown, subtract the mean, which is 100, divide by the standard deviation. To solve for x, I multiply both sides by the denominator, which is 16. 16 times 2.05 is equal to 32.8, which these cancel. The 16s on the right-hand side cancel to 1, and we're left with x minus 100. Add 100 to both sides, and we get that x is equal to 132.8. So essentially, if you want to be in Mensa, you have to have an IQ value that is 132.8 or higher. Verify our results for parts B and C against the graph. Are they reasonable? So we already plotted the 76 from part A. Part B was 138, so that would be probably around right here at 132.8. Now, if we think about it, 84 was 1 standard deviation away. 68 is 2 standard deviations away. So I can think of this as minus 1 standard deviation and minus 2 standard deviations. And what number is directly between negative 1 and negative 2? Well, that's negative 1.5. Okay, so hopefully that should make sense where it's placed. Now for the Mensa, we have 1 standard deviation here, 2 standard deviations here, and then a little bit more. Okay, so, oh, actually, I plotted this way too far. This was 132. 132.8 is like right here, which would make sense for it being 2.05 standard deviations away, because it's very close to 2 standard deviations away. 2.8. I can't write tiny with this pencil. I'm sorry. I hope you know that this is the 132.8 spot right there, really close to 132. And 2.05 is really close to 2 standard deviations. So hopefully that this makes sense, and you can verify that result. So in your book, you have these very large z-score tables, and these tables are going to be pretty imperative in order to answer a lot of these questions. And so what we can do is we can use the table of z-scores and z-values to find out the percentage of people who have z-scores below certain z-values. Okay, the way these tables work is that the z-score tells you the area underneath the curve for that section. It's a decimal value. All of these combined, like if I go all the way to the very, very, very end of the positive z-scores, they're going to be at 0.999. And it's implied that it gets closer and closer and closer and closer and closer to 1. Okay, because the area under this entire curve is equal to 1 because it's essentially representing 100% or the total of the data. So these decimal values can be interpreted as percentages. I hope that that makes sense. But essentially what you need to know how to do is read these z-score tables. So the z-scores are listed in the first column. So if I'm trying to find the area underneath the curve for a z-score of 2.5, I'm going to look in my z-score column, and I'm going to go until I find 2.5, which is down here at the very bottom. Now, there's more values. These got cut off. I would recommend you looking in the e-text. I might post a good example of a z-score table that you could use, okay? But we get the z-score value of 2.5. On the top, it has the additional decimal places. So is this 2.50, 2.51, 2.52, 2.53, etc., all the way until 2.59. So we first have to look in the column, the first column, but then we have to look at this first row and figure out what we're looking for. So if I was to look for 2.57, well, I'm going to be at the 2.5 here, but then I have to go to the 0.07 here, and then where those two match up, that would be my percentage. Okay, but since it's 2.5, which is implied 2.50, we're at this row, the last row, and we're down at this column. So where those meet, that is my percentage. So the z-score value at that point is 0.9938. We can change that decimal to a percentage by multiplying by 100, which gives us 99.38%. So that means 99.38% of the data is to the right of that 2.5 z-score. Check for the z-score of negative 1.5. So again, we're going to look at this column. We're going to look at these negatives, and I'm going to go to negative 1.5. There's no hundredths place, so it's just that first column after the z-score column. And so I get that that is equal to 0.0668. So then we multiply that by 100 to get our percentage, and so that's 6.68%. So that means that 6.68% of the data, if this is 0 and this is negative 1.5 as my z-score, that 6.68 of the data points lie under that curve in that area. Keep erasing. Okay. So I'm going to work through this problem. I know these are getting long, but I feel like you have to see several examples of them to really understand. And honestly, we could keep going a long time, but I'm just going to go through this one example, and then hopefully we get it, And then if you have more questions, you can email me or meet up with me on Blackboard Collaborate. So problem 1 tells us that the weights for 12-month-old baby boys are normally distributed with a mean of 22.5 pounds and a standard deviation of 2.2. So the weights are our variable. They are normally distributed with a mean of 22.5 and a standard deviation of 2.2 pounds. 2.2 pounds is 1 kilogram. That's just a fun fact. Okay. Begin by converting any given weight or weights into z-scores. Then use the table to find the percentage of a 12-month baby boy who weighs less than 25.8 pounds, more than 23.6 pounds, and between 19.2 and 21.4 pounds. So we're going to look at these weights, and we're going to convert the weights from this scale to our z-scores, which are centered around 0. Okay, whereas in this, we're centered around our mean, but we're going to relate it to a normal curve that's centered around 0. So what we have to do is we have to find our z-scores. So z is equal to our data value minus the mean over the standard deviation. Okay, so again, mu is representing the mean, and the sigma is representing, lowercase sigma is representing our standard deviation. So in this one, our x value that we're looking at is 25.8 pounds. Our mean was given to us as 22.5. And our sigma, our standard deviation, is 2.2. So you're going to subtract 25.8 minus 22.5, which gives us 3.3 divided by 2.2. When you divide that, you get 1.5. So our first z-score for this part A is 1.5. We're going to do the same thing for parts B and the 2 parts in part C. So I've shown the work for parts B and both parts of part C. Okay, so we get that the z-score that corresponds to each of these values, the first one is 1.5, the second one's 0.5, and then we get the negative 1.5 and negative 0.5. So what we're going to do is we're going to label the data items that are 1 standard deviation away, 2 standard deviations away, and 3 standard deviations away from the mean. We're going to then label the percentages. We're going to use this graph to verify the reasonableness of our results from part A through C. So based on the numbers that they gave us, the mean was 22.5. The standard deviation is 2.2. So when I add 2.2 to that, that gives us 24.7. Then we add 2.2, we get 26.9. And then we get 29.1. Then we subtract and we get 20.3, 18.1. And then essentially I'm just adding 2.2 for each value on the right for each of those standard deviations. And then I am subtracting 2.2 for each of the standard deviations on the left-hand side. Okay, so then we have our percentages. If we look at these values, 25.8 is halfway between 24.7 and 26.9. So our part for part A is very reasonable. If I look at 23.6, well, 22.5 and 24.7, 23.6 is exactly in between those, so part B is reasonable. And then we have 19.2, that's halfway between 18.1 and 20.3, which is -1, -1/2, -1.5 standard deviations. That one checks out. And then we have 21.4, which is halfway between 20.3 and 22.5. So that is half a standard deviation away from the mean. And notice it's negative because it's on the left. So everything to the left of the mean will have negative z-scores, and everything to the right of the mean will have positive z-scores. Essentially what we're doing here is we're comparing this to a normal curve centered around 0. That's where these z-scores are coming from. Okay, so our mean in this case would be 0, and then we have our 1, and we have our 2, etc. Okay, And so we're just figuring out and comparing on a perfect normal curve centered around 0, where would these values be? So, and then we use that chart to figure out the percentages that would lie to the left of these values. So here we go. We want to find the table to find the percentages of a 12-month-old baby who weighs 25.8 pounds. So 25.8 was here at 1.5. So we look at our z-score chart. I'm going to go back to look at that, and you're going to find 1.5. It's on the positive side. So that's right here. There are no hundredths place. So we have 93 or 0.9332. So the percentage for this would be 93.32%. Okay. So what percentage of babies weigh less than 25.8 pounds? That's 93.32. And that's essentially saying what's the percentage or the area under this curve that corresponds to that percentage. That area was labeled as 0.9332 in the z-score chart, and so therefore we can change that to a percentage. Now, if they had said what percentage is to the right of or greater than 25.8, that would be this side. So if I know that this side is 0.9332 and the whole normal curve adds up to 1, to find this area right here, we would have needed to do 1 minus 0.9332. And by doing that, that would give us our percentage for how many 12-month-old babies have a weight greater than 25.8. So then we do the same thing with the second one, more than 23.6 pounds. So 23.6 was at 0.5, 0.5 is our z-score. So then we look at our chart and find 0.5. That's right here again. No hundredths place means I can just look right there. That's 0.6915. Okay, so on this side, on the left-hand side, or less than that value, is 0.6915. But that means to the side that we're looking for more than that weight, we would take 1 minus 0.6915. So when we subtract that, we get that 0.3085 is the area under the curve to the right of that value, which means those are the percentage of data points that are greater than that weight that we were looking at. And so therefore, the percentage for B would be 30.85%. So we would say if we wrote that out in a full sentence, we would say 30.85% of 12-month-old baby boys have a weight that is greater than 23.6 pounds. Okay. Then when we're looking for, and this one's going to be hard because I need to erase all this and I've done too much, so it's going to be harder to erase. Okay, so for this last portion, we have a range. We're looking for the values between 19.2 and 21.4. So what we're going to do is the 19.2 was at negative 1.5 standard deviations. So I'm going to first in green find the area of that from the chart. So I look back and I look at negative 1.5 and we have that 0.0668. So this area is 0.0668. Then we're going to look at the area of the under the curve that's from the negative 0.5 z-score. So the area of the red part is 0.3085 and the area is 0.0668. So to find the area between those two, I would take the red and I would subtract the green. So when I subtract the green area from the red area, that leaves me with the purple area. So I get 20.2417, which is 24.17%. Okay, so that's how many babies would have the weight between them.